Mic off.
Okay. Announcements. Okay, as you all know, the lab exams today due by midnight. And the COVID institutional response survey is still up. It'll be up through Monday, the 11th. And okay, the next thing we have, last thing, big thing, is final exam. And that will be Wednesday, May 13th. And that'll be posted as usual by 8 a.m. and then due by midnight. And it's cumulative. The department requires a cumulative final exam because this is a transferable course under the Illinois Articulation Initiative. So it'll cover all chapters. So to study for this, study all the exams and quizzes and class notes, and it won't be as involved. Like it won't ask as problems or questions in as depth as in an hourly exam. So it'll be typically, I don't know, depending on the type of question, but you know, a few problems that involve calculations, or it could be maybe a half dozen or so if there's some multiple choice mixed in there per chapter. So it's more of a broad base coverage of the chapter, not as in depth as the regular exams. Okay, and then the class project is due the same day, Wednesday, May 13th by midnight. Wednesday's the last day of finals week. And then the writing assessment that will be included in the final exam. And I mentioned this last time, but I'll be posting instructions on Blackboard pretty soon. So it involves a short, like half page to 1 page example of your best penmanship, or not penmanship, but your best writing, your best prose. Okay, so I thought we could go over any questions you may have on the lab exam or the class project, and then we can review. I'll start with the last exam. The key is posted in Blackboard, but we can go over that. So are there any questions on the lab exam?
Mic on.
Okay, I thought I remembered receiving yours. So far I've received 3 or 4. Okay, how about questions on the class project? There's still quite a
Mic
bit of
off.
time to get that
Mic
finished.
on.
There's a week. And speaking of the class project, I looked into how to convert a string of letters, like a sequence, into a column, and one of the steps involves inserting a blank between each letter. And I think when I did that for the example that's posted on Blackboard, that I put a macro together and did it in Emacs. So since it's unlikely that all of you are familiar with Emacs, if you have a problem with that sequence and you need it converted from a string of letters to the same string but with a blank between each letter, then just send it to me and I'll convert it for you and send it back. It'll just take me like, I don't know, a minute or so to do that, because I already have a program set up to accomplish that. So just go ahead and send it to me and I'll send it back in the right format. Okay, so without further ado, then let's look at the
Mic off.
at the key for the last exam. That's not it, although it was used in it. There's the key for 2. Okay, here's the key for the last exam. Okay, the first part is chapter 17, electrochemistry. And if you have a question, just go ahead and interject. If you want me to skip ahead to one of your favorites, let me know, or one of the most infamous. Okay, so the first one involves a cell that's constructed with the She electrode on one end, and on the other side we have a half cell with the silver wire and AgBr solid is coated onto it, and it's in equilibrium with a solution that contains bromide ion. So this is a way to measure the KSP. So let's use this information and calculate the E0, well, not E0, the voltage of the cell. So you start out by setting up the standard reactions on the right here. This part here is the standard reaction. Silver is being reduced to the neutral silver metal, and that occurs at plus 0.8 volts. And then hydrogen's being oxidized into H+, that's assigned 0 volts. And if we multiply the top reaction by 2 to balance out the electrons, we get this net reaction here. And we use that reaction to construct the Q value. But to get the Q value, we need to know the concentration of the silver, and we do that with the KSP. So if we set up the KSP and solve it for silver, it comes out to 5 times 10 to the minus 11th molar. And then we take that concentration and insert it into the Q expression. It's a reaction quotient for this overall cell reaction. It's H+ squared on top and silver plus squared on the bottom. The pressure of the hydrogen's 1 atmosphere, so it doesn't do anything. It multiplies out to 1. So that ends up being equal to 4 times 10 to the 20th. Now that goes into the Nernst equation here. So we take the natural log of it, and even though Q is a really huge number, once we take the log of it, it dampens out the effect and converts it into a rather small number. So we get 47 afterwards. Then we take that and multiply it by 0.0257 on 2, and all that comes out to a minus 0.61 volts. So our cell voltage is 0.8 minus 0.61. We end up with 0.19 volts for this cell. Okay, and the second question is about a cell or 2 half cells. One involves gold being reduced to solid. The other is it's a standard, well, not quite a standard hydrogen electrode. It has the hydrogen gas at 1 atmosphere, but also a solution of HCl, a pH of 3.25. So if we take the reactions that are given and we cross multiply by 2 and 3 to end up with 6 electrons, but then these two reactions add up to the overall cell reaction, which is here. And for that reaction, the E0 value is a positive 1.5 volts. And the value of N is 6. N is a number of moles of electrons. And the 6 comes from cross multiplying up here by a 2 and a 3. So we ended up with 6 electrons on the left and 6 on the right, and they cancel out. Okay, so the pH is 3.25, so we can calculate the H plus concentration, which is 5.6 times 10 to the minus 4 molar, and that gets put into the Q expression here. And we end up with this. We substitute in the concentration of the gold ion, which is 0.18 molar, and raise it to the appropriate powers, and we get 9.76 times 10 to the minus 19. So that's our Q value, and that gets plugged into the Nernst equation here. So after taking the log of Q, we end up with a small negative number, minus 41.5. And after we do the multiplication by 0.0257 on N, where N is 6, we end up with a positive 0.18 volts. And that's added to the 1.5 volts that was the E0 value, and it sums up to 1.68 volts. So the the cell potential for the cell is 1.68 volts. The next one turned out to be confusing for about everyone. It was intended to be a simple thing, but I guess it's the interpretation of the C rate that made it confusing. So we have these discharge curves, which were measured by Duracell. And they have their battery, typically the capacity is listed right at the top in bold. This is what's printed on the batteries that you see in the store on the package and on the cell itself. So this is a AAA, and the capacity is 900 milliamp hours. So for this battery, the C rate is the current that's drained out of it so that it's empty in 1 hour. So that in all these curves, there's always one that has a service hour of 1. That's this one here, and that's called 1C. So their 1C rate is a current which drains this in 1 hour. So the current has to be 900 milliamps. So because to get the capacity, we multiply by the service hours, and we get 900 milliamp hours. Now, all the other rates are defined relative to 1C. The 2C rate, which is here, is twice as fast. So if we drain a battery twice as fast, we don't expect to get as much capacity out of it. So you can see the capacity, if we take 2C, which would be 1800 milliamps, and multiply it by however many hours it was, it's a little less than 0.5. We'll get a little less than 900 milliamp hours. But if we go slower, we can get more use out of the battery. If we go to 0.1C, that's 10 times slower. 1C is 900 milliamps, so 0.1C is 90 milliamps. And the service hours, we can estimate from this curve, come out to 11. So at 90 milliamps of drainage, this battery will last 11 hours. So we take the 90 times 11 and we get 990 milliamp hours. So that's the capacity at 0.1 C. If we went slower, even like 0.01 C, like we could get even more capacity out of it, maybe over 1,000. Okay, and the second part of this involved electroplating silver. So we take the capacity, which is in milliamp hours, and convert it over to coulombs. And a milliamp hour can be converted to milliamp seconds by multiplying by 3,600, and then convert from milliamps to amps, and we get amp seconds, which is a coulomb. An amp is defined as a coulomb per second. So if we take amps times seconds, we get coulombs. So now that we're in coulombs, we can use the Faraday constant to convert to moles of electrons. And then from moles of electrons, we can go to moles of silver here. And then we can go to grams of silver using the molecular weight, and it comes out to 4 grams of silver that we can plate out with this battery. Are there any questions on this? I'm curious what the main stumbling block was. So I don't think anyone in the class got it. Okay. Oh, okay. Yeah. Okay. Yeah, the milliamp hours is kind of different because we already have a unit of time in the amps. It contains seconds in the denominator. So we're like combining different units of time, but that's just how it's done. It's been in place for over 100 years, and it's really handy. Maddie, did you have any questions on this?
No, I'm good.
Okay, how about Victoria? Oh, she must have stepped away. Okay. Well, we could go on to the next part then, which is transition metals. Oh, did I mention? Yeah, you'll see something like this on the final. A lot like this question, very similar. Maybe not exact, but it's very similar. Okay. First question here is a coordination compound is formed from cobalt-3 sulfate and ammonia, and we're told that it contains 6 ammonia molecules as ligands. So we know that each cobalt ion is attached to 6 ammonias. So it looks like this. And it has an overall charge of +3 because each ammonia is neutral. So if this thing is going to make a sulfate, we would need 2 of these complex ions and 3 sulfates, and that's the answer in B here. So the answer to the first one is B.
Mic on.
The second one Okay, that's good.
Mic off.
The second one, let's see, we have an iron 3 ion with 3 oxalate ions attached. So here's an iron with 3 oxalates. And we know that oxalate carries a -2 charge. That's given in the question. And we're given that it's iron 3. So if we do the algebra, that means the overall charge of this complex must be 3-. And the only formula in the list that matches that is the first one, because there are 3 potassiums attached to it, and that would neutralize out the -3 charge and make it overall neutral. So the answer to number 2 is A. Number 3, we have a list of ligands, and the question is whether they can function as a chelating ligand, which means that when they attach to the ion, they form a ring. So the first 3 are out because those only attach in one place. The fourth one in D is long in the sense that it's a string of hydrocarbons, but it doesn't contain anything that could bond, like that would provide a lone pair of electrons. The only one that can do that is E. It has an NH2 group on one end and an NH group close to the other end. So technically it could attach in 2 spots and form a ring. So the answer to 3 is E. The next one involves naming these formulas. The first one is chromium attached to 2 chlorides and 2 ethylene diamines. And all of it's balanced out with 1 oxalate. Oxalate has a -2 charge. So we have the 2 chlorines, so we get dichloro, and then we have the 2 ENs, and we could say diethylene diamine, but that would be confusing because we don't know if we're saying diethylene, meaning 2 ethylenes for every diamine. So we put a bis there, and then in parentheses, ethylene diamine. And then the chromium has a +3 charge followed by oxalate. In B, we have 1 NO2 group and 5 ammonias, all attached to a cobalt, counterbalanced by 2 chlorides. So the part in brackets has to have a +2 charge. Nitrite has a -1, so that would give cobalt a +3 charge. So we have a 5 amine, so pentamine. We use the 2 M's for amine. And then we have the nitrite, and it's a ligand. It's not like a counterion. So it's a ligand, and we call it nitrito, followed by cobalt 3, and then chloride. I think most of you did pretty well on that part. Most of you got the next one too. The coordination number of the cobalt in this complex is, we can count up the ligands inside the brackets, and we get 6. So, and all of them are monodentate, so we have 6 for the coordination number. So the answer is D for number 5. Number 6, I think everyone got this, except for maybe 1 or 2. So the name of this complex is, we have platinum in the center. We have 2 amide groups and 2 chloride groups. And the chloride groups are close together. Like if we had a chlorine directly across from the other, that would be trans, but these are next to each other, so it's cis. So we have cis and 2 NH2 groups, so we get the diamine and 2 chloride, so we get dichloroplatinum 2. So the answer to number 6 is C. And number 7, here, this involves counting up the geometric isomers. And see, we're told it's square planar, so we can draw a picture of it. It makes it easier than if it were tetrahedral. So platinum's attached to 4 different ligands, so we can draw them out like this. And we can get a different compound if we swap places. Like, for instance, what if we swap the chlorine for the iodide? So if we did that, then the iodide would be directly across from ammonia, and that's technically a different compound compared to the first, where iodide was directly across from bromide. And the same goes for chlorine and ammonia. In the left, chloride was directly across from ammonia, but instead now it's directly across from bromide on the right. And if we continue and in the top position we put bromide, swap it with the one, like, actually it looks like we put bromide on top and then iodide in place of the chlorine. So anyway, all 3 of these are different compounds. They each would have different chemical properties. Because, like, for instance, in the first one, chlorine and iodine might not necessarily like being so close together. This might be more unstable than if they were directly across from each other, like on the right. So these would have different chemical properties. So the answer would be C, or 3 isomers for number 7. Number 8, we have a string of different osmium ions, and we're asked which absorb the highest energy light. So for the first one, we noticed it has ammonia, and then the other 2 more have water, and then one has bromide. And if we have a look at the spectrochemical series, we see that ammonia is a stronger field ligand than water, which is stronger than bromide. So that means the answer has to be A or B, because the stronger the ligand means the higher the splitting is between the energy levels, and that forces the light to have a higher energy to promote an electron. So for an electron to move from the lower level to an upper empty level, it needs more energy for ammonia than it would for water. Then, so the answer must be A or B. And if we look at the oxidation states, 4+ has a much more positive nucleus than a 2+. So we know that the more positive the cation is, the higher the energy is, the higher the splitting, higher the field strength. So the answer for this one is B. It has the strongest ligand, which is ammonia, and it has the most positive nucleus. Okay, number 9 here, it was, observed for 2 6-coordinate cobalt complexes. You have one with fluoride and the other with ammonia. The one is diamagnetic and one is paramagnetic. How many unpaired electrons are there in the paramagnetic? So let's draw energy level diagrams for these 2. They're octahedral, so we know the lower level has 3 orbitals and the upper level has 2. So altogether they can accommodate 10 electrons. So cobalt in its neutral form, ground state, is S2D7. And in each of these complexes, cobalt is +3. So in a cobalt +3 has a configuration of S0D6. So it loses both S electrons and one of the Ds when it becomes ionized 3 times. So we have 6 electrons to work with.
Mic on.
So for cobalt F6, we can populate those orbitals, put 1 in each level. You go across 1 here, then 1 here, and 1 here, 1 here, 1 here.
Mic
And the
off.
6th one goes back and pairs up. And the reason we can do that is because fluoride is a weaker field ligand than ammonia. That's from the spectrochemical series. It's weaker, which means the distance from the low to the high is smaller. That allows electrons to more easily populate that upper level, and we get a high spin situation. So we get the most unpaired electrons this way. So in this case, we have 4 unpaired electrons. And the other complex is cobalt with the 6 ammonias. That has NH3 has a high field strength, so the splitting is higher or larger than for the other. So the energy levels, which are empty, are farther away. And so when we populate these, we put 1 in the first level, then 1 in the second, then 1 in the third, and then we go back and double them up. The 4th one goes here, 5th and 6th. So we end up with this situation. None of them have enough energy to go populate the upper levels because ammonia is there. It's all ammonia's fault. So all these electrons have to stay paired up. This is a low spin situation. It's diamagnetic. So we end up with one being paramagnetic with 4 unpaired electrons and the other being totally diamagnetic. Okay. Any questions on this?
Mic on.
Oh, do you mean what's the correspondence between S and D over here and these 5 levels? Yes, right, they all do. It's all a matter of the shape, the geometry. It has to do with how the lobes point for the d orbitals on an isolated atom. Like cobalt has its own set of d orbitals. We have dxy, dxz, and dyz. And there are pictures in books. I'm sure OpenStax has one, or Jesperson has a bunch of them. But they're all pointing out in certain directions, and it's a little different from the other 2 d orbitals, which is d x squared minus y squared and dz squared. There's a much different look especially with the dz squared. So whenever 6 ligands come and they come at that nucleus or at the cobalt 3+ symmetrically, like they're trying to stay as far apart from one another as they can, so they come at it symmetrically. and it has the effect that these levels split. Like it's easier for the ligand to attach to the DX, Y, DXZ, and XY, or whichever ones. We have XY, XZ, YZ. Those three are on the bottom, and that's because they're easier to get at. The other two have a little more energy, so we end up with a splitting. That's the crystal field splitting. And how far apart it splits depend on what the ligand is. Like in this case, the fluoride happens to be weak compared to ammonia. Does that make sense? Well, that's something. That it's a rule of thumb. Just it's observed, and when you, it's a good question. You're asking why that happens, but to answer it, it's really an advanced question because it requires like a graduate level course to really understand why that's the case. But so the general rule of thumb is just matches up with what's observed in a lab in spectroscopy, because we know those s electrons have a little bit higher energy than the d, and they just are given up first. So that the first electrons cobalt gets rid of are the s electrons, and after that, then it starts pulling out of the d shell. And that's the case for all the transition metals. They lose the s first, then they go to the d. Oh, it's how many electrons remain afterwards, after we make the ion. Cobalt 3+ has 6 left in its valence shell. It started out with 9, it lost 3, so we have 6. Yeah, so we start populating this according to Hund's rule. We put 1 here. And then the next one goes here. It's the empty bus seating rule. And then the third one goes here. And now the question is, where does the fourth one go? Well, if the distance to the upper levels is small enough, then it could go up here. So we put the fourth one up here because the splitting was small, and that was because of fluorine. It's a weak field ligand, and it's small enough to where maybe normal heat could promote that electron and allow it to live up there. Normally that's not the case, and we have to hit it with light, like a laser or something, to bump that electron up. But in this case, the difference is so small that ordinary heat would populate it. So then the fifth one goes here. Then the last one, the sixth one, goes back down and starts pairing up in the lower level. It's hard to draw these to scale, but because it would look so cluttered, but really this upper level could be just a teeny bit above the bottom level, and it'd be easier to see why it gets populated. It's ordinary, like thermal fluctuations could cause it to populate that upper level. Whereas on the right, we have ammonia attached, and that's a strong field ligand. So we have a much larger splitting, and it's too far away to be populated. The only way we could populate that really is to either like heat it up to some extremely high temp or hit it with a light that's the right energy, and it would promote an electron up. But as soon as we turn a light off, it'd fall back down to where it came from. Wouldn't stay up there like it does on the left. Does that help clear it up? Okay. Okay, let's look at the next one. And actually, I just found out today this thing had a typo in it. It's a cut and paste error. This +2 here isn't correct. It should be a -4. So that means that half of this question really, that half of the points would get awarded for this, even if half of it's blank. So I guess that's good news for you all, right? I think this was one of the tougher questions, right? Okay.
Yeah, same here.
Okay. Well, the formula on the left was correct. So I'll look at that mainly, but the one on the right is not correct. But I fixed it here to show how the question would have been answered. Something like this will probably show up on the final without typos. Okay, so here we have a manganese, and it's kind of like the preceding question where up here we had cobalt attached to 2 different ligands. Down here we have manganese attached to 2 different ligands, and both of the manganeses are +2. And the first one, manganese, is attached to 6 waters, which are neutral. Overall, it has a +2 charge, so we know manganese is +2. And on the right, we have manganese attached to 6 cyanides, but if the formula were written correctly like this, like it should have been, then that would give manganese a +2 charge as well. So in either compound, manganese is +2. So if we look at the periodic table, manganese lives in the D5 column. So its configuration is S2D5. And then when it loses its 2 electrons, those are pulled out of the S shell, and we're left with D5. So manganese 2+ has 5 valence electrons. So we set up the orbitals like we did before for an octahedral complex. And in this case, water is the weaker ligand. So we get less splitting with water. That's less splitting means high spin, just like it did up here. This was less splitting, high spin. So in this case, here we have the same situation. So the splitting here is small, so these electrons can spread out and populate everything, 1 apiece. And we end up with 5 unpaired electrons, which is very much paramagnetic. And then for the other compound, we have cyanide, which is the strongest of all field ligands. So we know the splitting has to be very large in this case. So the 5 valence electrons are going to have to stay in the lower level because there's no way they have enough energy to populate the upper level. So we begin populating these with Hund's rule, that is empty bus seating rule. First one goes there, second one goes here, then the third one goes there, and the fourth one has to go here and not up above because that one's too high up in energy. It's kind of like, you could look at it like stairs. Like if over here on the left, like this looks from the side, that looks kind of like a staircase. If the steps are small enough, you know, a toddler could climb up those stairs. But over here, what if each step was like 4 feet above the other? Like only a giant could walk up those stairs. No one else could. They'd have to stay down on this first step, right? So it's kind of like that. So for this is a low spin situation. So we have the 5th electron being the only one that's unpaired. So it's low spin, and it's also paramagnetic, but it only has 1 unpaired electron, whereas the other compound has 5. So the one on the left is definitely more paramagnetic. And it all derives from the ligand it's attached to. The water is weaker, so we have a smaller split. That allows all 5 electrons to be unpaired. Any questions on that one? Okay, how about number 12? Here we have a diamagnetic square planar complex. Palladium with 4 iodides attached. Each iodide is -1, so we have a -4 inside the brackets. And we have a -2 outside the brackets, which means palladium must be 2+. So the ground state configuration of palladium is from the periodic table. Palladium's one of the precious metals, the stable ones like silver, gold, copper, and platinum. It's S2D8. To get 2+, we ditch the S electrons and we end up with S0D6. So we have 6 valence electrons in a square planar complex. And the right, what will charge on the palladium? Oh, good question. Did I misdraw this? S2D8. Yeah, I'm gonna have to fix this key. Yeah, good eye. Yeah, this should be D8. Yeah, I need to populate this one as well. Yeah, so, yeah, okay, I'll fix this. The principle, though, is okay, like as far as how the light promotes it. Like if we just pretend this 6 is correct here, then this is how the square planar orbitals would fill. And then if we hit this with light, it would promote one of the highest energy electrons to the next empty level. So we'd end up with this over here. Okay. Yeah, I'll get this fixed. Any other questions on this? Okay. Yeah, good catch. So you do understand this. Okay. Well, look, for everyone else though who didn't get this, if the absorbed light is at 595 nanometers, you look at the color wheel, and I have it somewhere, one of these tabs. There it is, 595. Here, have a look in this table, that's orange. So that's where the complex absorbs, and that's up here in this area. So to find what's transmitted, we take the complement. So we go straight across the color wheel to this area, which is blue. So the color that comes out of that beaker would be blue. Yeah, so the answer to part C is blue. Okay, we're at the end of chapter
Mic off.
19. Are there any questions on that? Any questions, Maddie?
Mic on.
Nope.
How's your cat?
He's great.
Okay, it's checking. Okay, chapter 21. The nuclear particle, which is described by symbol helium-4, would be an alpha particle. It's a helium-4 nucleus. It's missing both electrons. Okay, the nuclear equation for the beta decay of carbon-14. So we start out with carbon-14 and fill in the atomic number, which is 6. And if it's a beta decay, we know it's throwing out one electron. Here, this is the nuclear symbol for an electron. So to figure out what's
Mic
left
off.
has to be whatever's on this part here, which is the unknown. We're to figure out the sum of the protons has to equal left and right, so we must have a 7 here. So it's the only way we can get a -1 plus 7 equals 6. And then the mass numbers have to match as well. So we have 14 on the left. We have to have 14 on the right. So this must be nitrogen 14. And the next one is the alpha decay of U-238. So here's our alpha particle that's coming out. So to find what's left, we take 92 minus 2, which is 90. That tells us the element, that makes it thorium. And then we balance the mass numbers. 238 minus 4 equals 234. So the answer here is thorium 234. The next one is figuring out what the missing species is. We have an alpha decay of radium 226. So here, if we take the protons, balance them out, we get 88 on the left, 2 on the right. So we take 88 minus 2 and get 86, which tells us that it's radon. We balance out the mass numbers. 226 minus 4 gives us 222. So the answer number 4 is A. Okay, number 5, we have magnesium 23 undergoing some sort of process to end up at sodium 23. And it's conspicuous that the mass number is unchanged, but it lost a proton, and that's characteristic of electron capture, where the nucleus grabs one of the inner electrons and then it converts it into a neutron. So a proton disappears and is replaced by a neutron, and that's why the mass number stays the same, but the protons count goes down by 1. The way it would do that is in a reaction form is the magnesium here captures this electron. So we get 12 minus 1 equals 11, which makes it a sodium. And the mass number is 23 is unchanged. So the total number of particles in the nucleus stays the same. It's just that their identity is a little bit different. We have one less proton and one more neutron. Number 6. This is an application of Einstein's equation equals mc squared. So we're given the energy, and it comes from loss of mass. So this equation allows us to interconvert between mass and energy. So if we plug in the energy, which is given, and convert it to joules, and then divide by the speed of light squared, we get 1.03 times 10 to the minus 10 kilograms. So that's the answer to number 6. Then number 7 involves calculating a binding energy. And to do that, we need the mass defect as step 1. The mass defect is the difference between the observed mass, which is for this particular isotope, P31. The observed mass is 30.97 AMUs. And it's less than one would expect by adding up 15 protons and 16 neutrons. And that difference is the mass defect, and it's the mass that disappeared when the nucleus was formed. So here we add up the particles in the nucleus. We have 15 protons, 16 neutrons, and we also have 15 electrons, but those are 1,000 times lighter, so normally they're not included because they don't really change the answer to any significant level. So if we plug in the masses, multiply by 15 and 16, add it all up, we get 31.2477 something AMUs. And that's larger than the observed mass, which is 30.97. So we subtract them, and the difference is 0.0274. Or no, it's 0.274 AMUs. Now that is the mass that disappeared when the nucleus formed. And to convert that to energy, we just multiply by 931 million electron volts per AMU, and that gives us 255 million electron volts. Okay, number 8 is about radium decaying to radon-222, and it has a half-life of 1,620 years. It says that a 24-point-something milligram sample of radium was put in a time capsule in 1932. And with instructions to open the capsule and weigh it again in 2276. I think that date, 1932, was around the height of the Depression. Pretty sure. I think the worst year was 32 or 33. But anyway, so they're supposed to open it 300 plus years later, and we're supposed to figure out what the radium weight is at that time. So we can take the 2 years and subtract them, and we get 344 years. And we have to add in an additional half year because it starts on Jan 1 and ends on July 1, which is a 6 months difference. So we add the half year and we get 344 and a half years. So we can calculate how many half-lives have elapsed. We take the number of years, divide by half-life. So 344 and a half years divided by 1,620 years per half-life, and that gives us 0.212 half-lives would have elapsed. So now that we know how many half-lives have elapsed, we can figure out how the mass would have decreased over the years. So we take the starting mass and divide by 2 to the nth power, where n is the number of half-lives that we just figured out is 0.212. So we get 24.45 milligrams divided by 2 to the number of half-lives power. And that ends up being 21.1 milligrams. And in the list, that's B. Yeah, so the answer to number 8 is B. And the next one is also about half-lives. This one's carbon dating. Carbon has a half-life of 5,730 years. That is, carbon-14 does. So it says it has, let's see, the activity of this sample from mummy bones in a tomb has 60% the activity that living plants do. So we can take the mass, initial mass, whatever that would be, and multiply by 0.6, and that would be what the current mass is. The initial mass happened back whenever the bones were put in the mummy, or I mean, put in the tomb. So if we take the starting mass, or actually the current mass, present day mass, divide by the initial mass, we get 0.6. And then if we use one of the half-life equations, like the same one we used before, we start there and solve for n, and we get this. So n is equal to the natural log of m naught on m, all divided by log 2. Plug everything in, and we get 0.737, which is how many half-lives have elapsed. So if one half-life is 5,730 years and 0.7 half-lives have elapsed, you multiply that and get 4,220 years ago. So the answer to number 9 is C, 4,220 years. See, the last page is about applying radiation units. Were there any questions on the preceding? Okay, we'll just proceed. That's
Mic
number
on.
10. Number 10 is, what's the activity of a 10-gram sample of the beta emitter? It's rhodium 108, which has a half-life of 16.8 seconds. Now, the half, or the
Mic
activity,
off.
like what it's asking for is how many grams per second are disappearing. So obviously, the more sample we have, the higher the activity, because it's measured in grams per second. If we had a a ton of the stuff sitting there. A lot of grams per second would be coming off. So here we have 10 grams. So we take the 10 grams to figure this out. So that the half-life is given, and we need to convert that to a rate constant. And we do that by one of the formulas, which comes from kinetics. This one showed up in chapter 12, 13, whenever we did the kinetics. Like, it's related to one of them in the lab exam. I mean, we didn't actually need to use this in the lab exam, but it showed up in the same chapters. So if we solve this for K, K is equal to log 2 on the half-life, and that comes out to 0.0413 reciprocal seconds. So that allows us to get the decay rate. We take the 10 grams times the rate constant, and we get 0.413 grams per second. That's how much is disappearing per second. So now we can convert that activity over to other units, like to get decays per second. So we do that by converting from grams of rhodium to moles of rhodium, and we use that particular isotope, which is 108. So the mass is pretty close to 108. It's not the mass that'd be pulled out of the periodic table for rhodium necessarily. So then we convert from moles to atoms using Avogadro's number. That gives us atoms per second. And we know that there is 1 decay per atom here. So we end up with 2.30 times 10 to the 20th decays per second. And that's a becquerel. A becquerel is defined as 1 decay per second. So we've ended up converting the decay rate to becquerels. So here we can convert becquerels to curies using the conversion that was provided. It's 3.7 times 10 to the 10th becquerels per curie, and we end up with 6.22 times 10 to the 9th curies. So that's the answer to number 10. Okay, number 11. It involves converting the exposure limit for whole body dosage, which is approximately 500 millirems per year, to other units, like joules per kilogram. So to do this, we do a unit map to start with. We would end up converting a millirem here to joule per kilogram, which is equivalent to a gray. So now the millirem is a biologically effective dose, and that's given. It's 500 millirems. But to convert to the other units, we need rads. We have to use rad as a stepping stone to get to grays. And the actual dose here, AD, or absorbed dose, is measured in radians, and that's multiplied by the equivalent, the RBE, which we choose from a table that's given at the end of the lab, and it says general public here. So the general public would be exposed to an RBE of 1, which is like a beta decay or X-rays and things like that. So we choose RBE as 1 and then solve this for the absorbed dose, and we get 500 rads. and then convert the 500 rads to grays, or 100 rads per gray. And a gray is a joule per kilogram, so we're finished at this point. And we end up with 5 joules per kilogram, or 5 grays, which is the answer to part A. So that tells us how much energy was absorbed per kilogram of tissue, but it doesn't tell us a lot about how much energy it impacted the tissue with, kind of like whether it was a softball or whether it was like a major league fastball, like how deep did it penetrate. So to do that, we need to know the voltage that it was impacted at, and that's given at 5 volts here. So we can convert to Roentgen, take our 5 volts, or no, this is the 5 joules per kilogram. That's the grays that we came up with in part B. And then we use the 5 volts, which is a joule per coulomb. So this part of here is the 5 volts. We're converting joules to coulombs. So the joules disappear and we're left with 1 coulomb per kilogram. And that can be converted over to Roentgen with a conversion factor that's given in the back. So we end up with 3,880 Roentgen. Then the last one is about someone who's exposed to a source of low energy protons. It is about on the order of thousands of electrovolts at an energy of 8 volts, and they absorb 0.15 Roentgen. What is their exposure in units of millirem? This millirem is the typical unit that is used in the workplace, like when people walk around with a little badge attached to their shirt. It is absorbing, and it's measured in units of millirem, and that's where the 500 comes in, that it's not supposed to exceed that per year. If it does, then they need to change their work duties or adjust them so that they're not absorbing anymore for that year. So here we can take the 0.15 Roentgen and convert to coulombs per kilogram, and then convert from the coulombs to joules using the voltage, which is 8 volts. And we end up with 3.1 times 10 to the minus 4 joules per kilogram. And then we convert that to grays, and from grays to rads, and we end up with 3.1 times 10 to the minus 2 rads. And that's the typical unit that an absorbed dose is measured with. And now we can use the RBE equivalent. And in the table that's provided for dosages, or I mean a source that's on the order of KeVs, we are in the range of 2 to 5. So if we take an average of that, let's say 3.5, that's what we would use for the RBE. So to get the biologically effective dose, we take the rads times the RBE of average of 3.5. We get 0.108 rems, which is 110 millirems. So 110 millirems is the answer to to number 12. Then the very last question was extra credit about whether or not glass is a liquid. And Just about everybody. I think everyone put false. Technically, it's not really for sure known, but it's fine if false was put. I think more people think it's false than true, but there is evidence that glass flows. It has a viscosity just like oil or honey or water. So it does flow over time, which is characteristic of a liquid. And it's amorphous, but being amorphous doesn't make it not a liquid. I mean, we have amorphous solids, but those solids don't flow like glass does. So yes, glass is amorphous, but it does also flow, and some well, I had always heard that the old chapels built in the Middle Ages have the stained glass windows, and that if one looks at those panes from the side, the top will be really thin and the bottom will be thick. And that's because the water flows down. I mean, the glass flows downward over the years. But others say that the casting process they used for those panes back then always ended up with a thick end and a thin end. And that, the reason that it's thick on the bottom and thin on top is because it was made that way. But on the other hand, there's no way they would install a pane of glass that was so thin at the top. It's like paper thin and it's really easy to break. If it's just tapped lightly, it'll crack. They've had to repair a bunch of these. So I think, yes, it was made with the bottom thicker than the top, but it also flowed some over the years. So there is evidence the glass is a liquid, but a lot of people think that technically it's not a liquid. So the answer to this is false, but if you put true and gave a reason, then that'd be fine as well. Okay. That's about it. It's the end of the exam. Were there any questions?
Mic on.
Nope.
Okay. Okay. How about any other chapters? Is there any other part you'd want to see looked at? How about you, Maddie?
I'm good.
What about your cat?
He's good. He just wants me to pass.
Oh, okay. How about,
Yeah, same here.
okay, I'm going to turn the recorder off. Okay, well, I'll post this link.